Which one?
This one here, I think.
Okay.
I just did something.
Okay, anyway, people will be around if there's a problem with
exactly.
stuff like that. I mean, let's see, I probably can click on the one, go to Mast and that one, but then to go to Sundog itself, is that,
I suspect if she's gone there before, it'll give her the password.
then it would be in her,
Yeah. Jan?
okay.
Brad was wondering to get to Sundog, the non-public one, you've got it set up with the password in already and all that.
You can just share your screen.
But you were having problems with your laptop.
Well, I'm worried about that. Let me try to bring it up and see.
If all else fails, you can use mine, Brad.
Yeah, I mean, if you want to set it up there. So the boss tells me that we'll start in 2 minutes. So, but those of you who have arrived, everyone's new best friend is Kirsten. She's the She managed to print out 50 copies of the montage of 19 galaxies. So please come and see her if you want one. Do you want to?
I already ran out.
You ran out already?
Yep.
You good to go? Oh, okay.
Welcome everyone. Symposium is over. Now this is workshop time. So we start with the Franks group who are going to present exploring the Franks treasury dataset using multiple facilities. So
Thank you,
Janice, take it away.
So several people have reminded me to introduce myself because I did not do that on first 2 days. So I'm Janice Lee, if you don't know me, and I'm staff here at the Institute where my functional role is working on trying to make Habel World Observatory happen. So I'm a project scientist for strategic initiatives. On the research side, this is where my life is with these wonderful people here in the room. It's realizing the idea behind this entire conference, which is to study star formation on a multi-scale, in a multi-scale context. And so what you're seeing here is one of the first galaxies that we've observed with JWST. It was just a few weeks after commissioning was over, and it's NGC 7496. On the QR code, you can go to the web page that we've set up, and we released a lot of our data sets just this past January. So we'll take a look at that. But I'm just going to say a few words, not so long, to introduce our brilliant team, and then give you a little bit of context for why we're doing what we're doing, and some other references that might be useful. And this is a workshop. At any time, please stop me. If you have a question, just raise your hand. Or I'm not sure if anybody's monitoring the Slack anymore, but you can also put it there and tag us, and then we'll go and try to look for it. And if you have questions, follow-up questions, please. I know some people would rather ask questions on Slack. We'll go and look at it after the workshop as well. Okay, so let me change this. So that was the NGC 7496 was one of the first galaxies observed, and you can see it's a spiral galaxy. And then a month later, this image, which has taken a life of its own, was delivered to us in August, just a couple weeks later. And the point of this slide is not only to show you a beautiful image, but to share with you our charge as a Treasury program. So we not only carry out our own research, but as one of these treasury programs, a very large program with either Hubble or Webb, we are making a commitment to the community to support a broader range of science. What that means is that the data, they do not have an exclusive access period. Once the data come down, anyone can download it. And that was what was just so thrilling about the first few months of our observations with Webb. People, not only astronomers, were downloading the data and making their own color images and posting them over all over social media. For this audience, you know, if these images appear a lot of places because they're good for talks, but you know, the data are also there. And we've had many conversations with individuals about how they want to use the data for their own research. And I hope this workshop gives you insight into what the products look like and gives you a chance to ask some questions. So if you go to that QR code, it leads you to this page. This is a MAST page that provides the higher level science products for our program. And at this page, you will be able to not only get the reduced data, the mosaic images, but you'll also be able to pick up catalogs, which we'll talk about later, catalogs of 100,000 star clusters and associations. What's new about this site is that it's also it's linking back to the public outreach images that were released in January. So you can see one example here, NGC 5332. I think this is also up on the screen when you walk in. But our public outreach office has done a phenomenal job of not only creating color images, but also, you know, these split Hubble and Webb images that really tell the story of the star formation cycle and why you need multiple space observatories working together to tell that story in one shot. Okay, so why are we doing this? Well, it's one of the reasons why we're all here at this conference. We want to understand how stars form from gas, but in a galactic context. And of course, the issue has been, if we want to understand star formation, we have to study all different phases of the star formation process. We have to study it on all different scales. And that's what has made the problem so incredibly difficult. And we have to do this for observations and simulations. We're trying to answer the question of what controls population growth, not necessarily how does an individual star form from a gas cloud. And so these are the questions that the FANGS group, our collaboration, are trying to answer with this data set. We have grown to become an extremely large, one of the larger collaborations across, 5 different continents. We have over 150 members now. And here you see the principles of the survey. Ava Schinnerer in Heidelberg, MPIA, is the PI of the overall collaboration. Adam Leroy is the project scientist. We have Eric Enslin, who led the MUSE observations, and Eric Rusolowski, who is the team manager. And the reason why we have all these people is because we need all these facilities, again, to capture the multi-phase, multi-scale nature of star formation, so we can actually make some progress on those questions. I won't go into very much detail here because this will also be in Dave Zilker's talk, but an overview of the sample is that we have 90 galaxies with ALMA observations to capture the molecular gas. With HST, we've completed observations for 38 galaxies, and that's what you'll find on that website where the QR code leads you. With MUSE, we have 19 galaxies, and then with JWST in the first year, we also have 19 galaxies. So it's for 19 galaxies that we have the full span of ALMA, MUSE, JWST, and HST data. New programs this cycle, we were so incredibly blessed. We won the lottery like 5 different times. They extend the JWST and HST observations to 74 galaxies, and those are led by Adam Leroy and Dave Zilker. If you want to see what we've been doing with the JWST data, I think in the first few months, everyone went a little bit crazy because the data were just so miraculous. And so we have a focus issue that we published for AppJ Letters with 21 papers on all of the key topics, including on the results that Jimena presented today. So from dust-embedded star clusters to the dust filament network, we have papers on feedback and this really intriguing idea of using the dust emission as a total gas column tracer, and then insights into PAHs at 3.3 microns especially, because it's the first time that we're being able to study it on these scales in the nearby universe. So for today, that's the overview of the entire survey, the entire program across all 4 facilities. Today, we're mostly going to focus on the star clusters and multi-scale associations. And as I mentioned, a lot of this data was just released in January. We also have 2 companion papers, and Dave will talk more about this. But Daniel Maxman, whose poster is now gone. Is there though? Well, okay. Wave. His paper was accepted, and it provides an overview of the observed properties of this very large sample census of 100,000 star clusters and associations. Dave will talk a little bit about, okay, so we've got the photometry, how about the ages, the masses, and the extinctions, and the challenges in deriving those. Okay, so last couple of slides, we just really do have to acknowledge the incredible teamwork that it required, even for just the JWST and HST data, to bring the community this data set. So this is the Stellar Populations Working Group within the FANGS survey. Okay, postdocs are laughing up here. What's so funny? Is there something wrong with the, no? Okay.
Brad looks very young there.
Oh, I see, right. Actually, yeah, there are various look-back times for each one of these pictures here. What's redshift is that? It's cosmic noon. Anyway, our Stellar Populations Working Group works within the Greater FANGS collaboration, and these are the folks here for the products you'll be seeing today. It was 3 to 4 years of work, and so I just wanted to recognize Dave Filker, who will be speaking next on all his efforts on the source detection and candidate selection pipeline, along with Brad Whitmore, a recognized expert in cluster study, who visually classified, 30,000 individual clusters that we then used and encoded his brain in a convolutional neural network so that the convolutional neural network could classify the morphological properties of these clusters that are in these catalogs that we're delivering to you, that we've delivered to you in January. And then other people in the audience, Kirsten, she's been leading on associations. She'll provide a tutorial on how to access those catalogs and how to work with them. And then, of course, Daniel here, who without his efforts we would not have had the delivery in January. So, anyone else? Okay, so, go back. I just wanted to say one word on how we imagine the cluster catalogs to be used. And on the left-hand side, you see a color diagram. It's UB on the vertical axis and V minus I on the x-axis. And all these tracks that you see, they're of a simple stellar population, right? Single age. So everything forms in a single burst instantaneously. Young is at the top and then old as the bottom. So 1 million years is up here and the age of the universe is down here. This is an initial sample of when we were just getting started, what the 2D distribution looked like in this plot. And then Daniel has shown in his paper and in his poster, this is what the plot looks like. The 2-dimensional distribution of clusters, 15,000 of the brightest clusters from our catalog of 100,000. And so there's all sorts of science that we're doing with this sample. But for folks who are working on clusters, not only in the local universe now, but even, 500 million years just after the Big Bang, one of the useful things you could do with this plot, after you have the notebooks and can plot up the distribution, is to ask, where do other cluster samples fall in this diagram? Because it represents a lot of evolution, not only of clusters, single-age populations, which underlie all of the work that we do when we do SED fitting to infer the physical properties of galaxies, but to also track how clusters and even just stellar population models are evolving over time. This one is just solar metallicity, so what we see today. So where do other cluster samples fall in this diagram? And then another thing that you could do with the notebooks is to overplot different population tracks. So I'm only showing one here and a few here, but this distribution really does constrain our underlying simple single-age stellar population models. I think with that, does anyone have any questions? So I see a whole bunch of people with laptops, so there's going to be notebooks presented. If you have laptops, would be good to get them going now.
Yeah, I put links in the Slack for the notebooks.
In which Slack?
Our workshop Slack.
Okay.
Yeah, the name of the channel is Workshop 1 Fangs Pinab.
It's going to give a bit of an a little more details before we do the notebooks. But yeah, while Dave's getting set up, I'll just say the notebooks they run in something called Google Colab. So the link will take you to a page that you can just run the Jupyter notebook in that page. You don't have to have any Python loaded into your computer. It should run. Yeah. You can add the Slack channel. So if you're on the, okay. I'll put it in the Space Telescope Slack. Yeah, and I'll email people that I know don't have it. Go ahead, Dave.
Thank you, Kirsten. Okay, so I'm going to try to give you a whirlwind overview of our products for these 4 different surveys. And as Janice explained, we'll have a focus on the HST and web products a little bit. But so this is going to be the outline for the rest of our time, just a summary of the status of the surveys. Brad's going to do an interactive viewer demo, and then we'll have 2 separate notebooks, one devoted to the clusters, one to the stellar associations. If there's time, we'll end with a demo of how you can connect DS9 and TopCat to make it really easy to inspect specific objects in an interactive way. I also wanted to point out that Janice had already given the 2 links that are down here in the bottom, but there's also all of the FANGS data products, so across all the surveys, are available at this, if I can find the pointer here, at this website. It's really quite useful. Things like environment masks, other far UV imaging from Astrosat and so forth. So everything that you would want from FANGS is at that top link. Okay, so I'm going to skip this, honestly, because I didn't expect Janice to show so much. So basically just say a brief comment here that we have all of this fantastic small-scale information, and the ultimate goal, and not only is to know how physics and star formation works on those small scales, but how it adds up together to perform, to get the integrated properties of galaxies as a whole, that people that maybe aren't at this workshop working with integrated photometry to help them understand what they're seeing. And to do that, we obviously have the multi-observatory approach, doing ALMA with the CO, Webb with infrared, and then star formation with HST and with the MUSE integral field unit. Okay, so I don't believe this was shown yet, but this was our sample of 74 galaxies. So the entire project started with ALMA. That's why we have up to 90 now with ALMA, but these 74 are special because they will all have the ALMA observations, HST and JWST obtained within a year from now. They're generally more southern galaxies, obviously because of the ALMA beginning, and they were selected to be nearby so that we could resolve the individual star-forming quanta. They're also face-on so that we can see them better. The properties on the galaxy main sequence here are, we're probing basically from 9.5 in log of stellar mass. I see the label didn't show up. This is stellar mass on the bottom, and going up to the massive end of the star formation main sequence. So it is representative of the larger galaxies in our local universe, but we don't probe the dwarf population very well at all. That is really the forte of the LEGIS survey. Okay, so what do the CO data look like here? This, I'm not going to go into any detail at all except to point to this paper by Sophia Stuber, who did morphological classification of the entire FANGS ALMA sample and picked out things like the flocculent galaxies, multi-arm, grand design, and so forth. But the number of galaxies presents you from being able to see the fantastic quality of the data, and that's what this slide is for, and showing this is basically the resolution that people would get before ALMA came into being. And then this is an example of the transformative resolution increase that we have. Arc-second beam basically corresponding to under 100 parsecs for the entire sample of galaxies at high spectral resolution as well. It is sensitive also that basically if there is a typical GMC located within the beam of our survey area, it will be detected, working that into, rather than molecular gas surface density, working that into a mass for the cloud. You can see that it ranges, this is the 1 sigma limit, so obviously multiply these by a couple, but we're getting down to GMC sizes that are related to the formation of individual clusters. Let's see, so this is just to show you a little bit more of the CO data. So not only do we get the column density maps, we get things like the velocity field. This is the line width of the CO line. And we have this now for 90 galaxies. So it's a fantastic resource for the community. All of these cubes, the maps and so forth are available at that Google site that I told you about. Okay, but the focus of this was really supposed to be more so on HST and on JWST. I do want to point out that the observations from MUSE are ongoing. We have proposals in to try to get the rest of the sample obtained. But this graphic that I'm showing you here, there's a link for each of the programs that provided the various pieces. So if you want to know more about what we're hoping to do with a certain subset of the observations, you can follow those links on the PDF that we posted. I just wanted to point out in terms of the newer observations, we originally just got the 5 broadbands with HST. We're adding H-alpha for all 74 of them. With James Webb, we're adding these filters, so higher resolution F150W, also Passion Alpha. This came at the cost of some of the other more comprehensive choice of filters that we had for cycle 1, just because instead of doing 19, we're doing 55 galaxies, so you can't ask for everything. And from the initial observations, these were the ones that were most useful for our studies. Okay, and then we got lucky again in cycle 3, and Eva Schennerer is leading a program on the centers of 16 of these 74 galaxies, getting bracket alpha deeper in the 3.3 and the Passion Alpha features, iron 2 emission, and the molecular hydrogen for the starbursty rings in many of our galaxies. So I wanted to spend a brief moment here describing the reason that we're going to the H-alpha observations from Hubble. And you can see at ground-based resolution, you would have a hard time linking any one of these specific clusters to a component of that integrated blob that you see. But you can do that once you have the resolution of HST. Also, we're adding the Paschen alpha lines. This is just a ratio map of H alpha to Paschen alpha for an H2 region complex, showing that the line ratio and the extinction does indeed vary within H2 regions. Okay, for the Muse data, I see I'm running late on time already, so we're going to speed up here. We have all these different lines that tell us about the ionized medium and its properties. I'm going to skip a little movie that I had here that shows the evolution through an IFU cube with the different lines. But I wanted to point out that we're in the process of preparing derived quantity maps, like the velocity fields of the stars, the velocity fields of the ionized gas, stellar mass, surface density, age, and stellar metallicity. Those aren't available yet, but they will be hopefully in the near future. Okay, so finally I got to the HST stuff. So I'm hoping to convince you that we have a revolution in extragalactic cluster and association science because of the uniformity with which we've done these observations, the uniform way that we've processed them, and just the number of galaxies in general. We're going to use these as cosmic clocks to time processes and as power meters to gauge the input of feedback into the ISM. I wanted to point out that these numbers, though large, are only for the first 38, so they will be doubling by a year from now as well. The SED fitting that we use, I'm only going to briefly go over it. It's using a special branch of the Segal package, and we're in the process of starting to blend in the Webb observations already for our near IR bands in particular. Okay, so this is way too much to explain in detail, so I'm just going to give you the highlights, but I wanted to flash this up to give you an impression of why it took us 4 years to get to the stage that we're at. This shows the flow from the raw observations through the photometry and detection stages, cluster candidate selection, the classification of those cluster candidates, and the watershed analysis that leads to our multi-scale stellar associations. And I'll spend just a little bit of time explaining some of these bits. So we made the choice early on in the project to have a common origin of detection for our clusters and for the stars that are used to build up our multi-scale stellar associations. So everything really begins with Dolphote. We produce a source catalog with PSF fitting. Right away, we feed that off to the identification of these associations. But then we add further extended sources using PhoteUtils to get an all-source catalog. And that's what we use to begin the process of selecting cluster candidates. Now, in the past, for LEGUS and for decades, actually, people have been using the concentration index, so just the difference in magnitude between the photometry you get with a small aperture and a slightly larger aperture to select things that are more extended than point sources. We decided that we have more information, we should try to use it. So effectively, we created new metrics, what we call the multiple concentration index for the inner part of a source and for the outer part. And it essentially measures the similarity between the profile in those radial regimes and what you would expect for a nominally, some fiducial cluster, basically. And the way that we use this is that we empirically defined these linear-looking polygons here based upon previous catalogs of clusters, so we knew where things would lie basically. And then we did synthetic cluster computations for a wide range of various morphological parameters in order to get a more comprehensive idea of where things might land in this plane, and to allow for the fact that there might be clusters that were not in our previous empirical sample, different types of morphologies. And the red dots here, I should say, those are candidates that were identified because they were so bright that we knew they couldn't be a star. They were above V magnitude of -10. So with that, I'll go on to the classification. Like Janice said, Brad looked at tens of thousands of clusters. We used that to train a neural network using deep transfer learning. And this is the accuracy that we're getting now when you have our subset of the FANGS classifications. We use it to train the model and then evaluate the accuracy on a control set. And we're getting 70 to 60% accuracy on the classification for particular morphologies. And that is equivalent to what humans that are individually trained and doing the classification themselves, what they also get. But I wanted to point out that the cluster-no cluster choice is actually quite a bit more solid. You know, we're getting 90% accuracy on whether something is a cluster or not a cluster. Okay, Kirsten will talk about this a little bit, but as I said, we use the distribution of point sources from our initial Dolphote run to generate density maps of a tracer population at different scales, do watershed analysis within those density maps to get nested, hierarchically nested structures that we identify as associations. So moving on, what do the clusters actually look like? This is just to give you a context for I believe this is the brightest cluster in each of our 38 galaxies. The range of morphologies you can pick out in the environment is quite stunning here. You go from things that are clearly old globular clusters to objects in young star-forming regions. So we're picking up a comprehensive set. But we have so many of them. That's one of the points I want to try to make, is that this project is taking the study of extragalactic clusters into what I like to think of as a Sloan kind of context. You know, for galaxy evolution, having that many objects detected and studied by Sloan allowed transformative science, and I think that will happen for us as well. This is roughly 1/50th of our set of clusters. This is what the stellar associations look like. I'm plotting here 3 different physical scales. You can tell by the color, cyan is the biggest scale, and then dark blue and that purple magenta color. But the point I want to make is that this is an equivalent representation of the associations, you know, within a few kiloparsecs of the sun, put at the same scale. So we're getting so many objects that are essentially equivalent to the galactic case, but we can study them in the context of where they live. Okay, this just shows you the NUV sources that we use to do the definition. So just a couple words on the SED fitting, given I'm running out of time, and I'm going to stop that before it beeps. The evolution of these clusters in a color diagram, V minus I versus U minus B, things start at a few million years old in the upper left-hand corner, and by 10 million years they've reached this excursion, which is associated with the population of red supergiants, and then they gradually age down to a few giga years, and then the age of the universe. And you can see the same evolution in the SED shape with our 5 HST filters overlapped. But the problem is it's not as easy as this, because this allows for no dust and no change in metallicity. So once you allow for the fact that reddening can move a cluster from having no dust down to 2.5 magnitudes of AV, you can't really tell the difference as easily between something that is here because it's dusty, it really belongs up there, or something, you know, that is down here, 20 million years old and has no dust at all. But there's this degeneracy, even with 5-band photometry. And it's made even worse in the fact that you have this purple line is for low metallicity globular cluster-like models. They could be misinterpreted as a slightly dusty 100 million year old cluster. So we've gone to great lengths to try to address this, and the approach that is being used now is to do SE fitting with focused model grids. So we used extra information, like whether or not a source lies, for instance, smack dab on an H2 region that we see with HST, to guide objects through a decision tree. I'll try to go back here. So things that have H alpha go up here and they're considered to be young likely objects, and then we do some other checks on them to put them in this young grid. So models only allowed of a few million years where you'd be expecting to have the ionizing luminosity. If you don't have H alpha, they go down into a separate branch, which eventually feeds a low metallicity grid. And we do actually have additional checks. If I can make this go further. We know from Daniel's work that globule clusters heavily populate this part of the color-color diagram. So in addition to not having H alpha, we do a check on the color-color location to make sure that things that we're saying are likely old and forcing to go into that old model grid are consistent photometrically before we do that. And in the paper that will come out hopefully before long, hopefully you can read much more about this, but the point is that we are for once able to get age mass diagrams, reddenings, and so forth for this entire set of galaxies done uniformly. We recover, this is age on the x-axis, mass on the y-axis. You can see a lot of these enhancements at the age of the universe, roughly. Those are the globular clusters that in almost all previous studies would have been interpreted as highly reddened young clusters. And so having this new approach to the SED fitting allows us to do better at both ends of the age range, basically, to study the globulars in their proper context, and then also to understand potential changes, for instance, for the age distribution function at young ages once you remove those contaminants from the population that you're measuring. I'll just spend a moment on this. Each one of these is an age mass diagram put in kind of a smooth format instead of individual points. And we're plotting these diagrams with respect to position on the galaxy main sequence. And I don't have time to explain it in full detail, but I hope you can appreciate that the type of age mass diagram changes as a function of where you are with respect to the main sequence. You get obviously bursty things with a dominant few 100 million-year-old population above the main sequence. You get objects like 45, 48 down here that essentially just has old clusters below the main sequence. And with that, I'm going to pass the baton to Brad, who's going to talk to you about the Sundog interactive viewer that we have.
In the interest of time, let's just go to the link, the mass link.
Yep.
I'll show them what and where the interactive display is, and then you can kind of look at it yourself.
could. Or do you want the public
Go
one?
right to MAST.
Okay.
Yeah, I mean, it was the top link.
It's okay if you all want to take some additional time. I probably need like 25 or 30 minutes to take some extra time.
Let's see which one.
That would be fantastic.
All the big material, so that's totally fine.
Is that Ryan? Thank you, Ryan.
Just hit the top link.
While they're setting up, does anyone have any questions? Any questions at all, even very basic ones?
you
And
want-
what's the,
This is the laser here, the green line.
okay. Okay, so the interactive display is one of the tools we use a lot. If you've heard of the Hubble Legacy Archive, it's that software that Rick White is primarily responsible for. And so it's already linked, kind of a dumbed-down version, if you will, in the math site that Janice showed you. Whoop. So why am I not? There we are. Okay. So if you just go down and like where you'd want to get the data access, and you go to the data tables. Okay. And so here's where you would get the data, but here you see the little interactive display. And so let's just go down to one of my favorites, 628. Okay, hit interactive display. There we go, I guess. Nope. Okay, that now going to work then? Oh, it's starting to come up. Yeah, it was C. It would be the better one. Okay, just go back to your view graph, and I'll just, oh, okay. So here's the interactive display, and so it's, like I say, it's a dumbed-down version, okay, where you've only got the 5 filters here from the HST. So the updated version will have all the JWST bands, also has the CO from ALMA, etc. It does the kind of things you'd expect. You know, you can kind of zero in. Change the display. Contrast. And in the view graph, when we go back and look at the various things that the Hubble Legacy Archive software can do, it's probably going to take too long to load here. Okay, yeah. So other things you can do, it can also, besides kind of mixing the different colors for you, there's advanced contrast control, so you could really make, you know, any image you want with all the different filters combined. So that's very nice. Why don't we go back to that view graph? Actually, I'll just point to 1 or 2 other things. I think this is going to be too slow to load. There we are. Okay. So the kind of things you can do with the advanced contrast I was talking about here. So you can really make quite spectacular figures with all the different wavelengths. You'll have all 15 bands, including CO. It overplots the various catalogs you've heard about. What we call the human catalog, namely me, and the machine learning catalogs also. And then if you just click on that, then you get kind of a quick look at what's in our tables. For example, this object right here on the edge of this nice H2 region has an estimated age of 1 million year. You can get cutouts, which can be extremely helpful. You can kind of insert that into your own programs. And I guess that's most of it right here. So why don't we stop there, and so we can move on to the notebooks. There is a paper that explaining the Hubble Legacy Archive from 2016, so a little out of date. And this just, when you go to that site, it's going to be that dumbed down version which just has the 5 filters and doesn't plot the catalogs yet. But that's likely to come along when? Couple days. Okay, very good. Why don't we move on then?
Just curious, can you raise your hands if you've used this viewer before? Has anybody had? Oh, that's cool. All right, so at least a few people in the audience. The nice thing here is you don't have to install anything. You don't have to download the data yourself. It's all within the browser. So does anyone have any questions? Okay.
Switch computers here.
Do I have something to scroll down? Okay, so I think it will be, do I have something like a, yeah, okay, mouse pad. Yeah. So I would like to run you now through a notebook which is in Python and just downloads our data and just does very basic things with it. So the aim of this is to provide these data products and show you an example how, for example, if you have a galaxy, which happens to be a Fangs galaxy, that you know, okay, I know where I can easily access the data, overplot where are the clusters are, what properties they have. As said before, there will be soon also SED-fit catalogs. And yeah, so I think I don't really have to tell you how to load some modules. I wrote a small script with helper functions in there. I'm just like downloading here from my Git repository. So this should be all fine. And here, like in the next column, I'm making the example with NGC 1097, which is a galaxy I quite like. And why is it clicking? Sorry. Okay, so it is wait, I want to show. So here I have 2 links. One is for the catalogs, and one is for the images, and where all the data products are listed. You can download each catalogs for all the individual galaxies. However, in the next panel here, I'm just downloading them in a manner you can also download them in a local Python script. You don't need to have this like via Jupyter Notebooks. And sometimes to download stuff in Jupyter Notebooks, there are like quite quick hacks you can use. This will also work in your normal on your local computer. Okay, so here I'm just like making sure that the naming is correct, because now we are downloading also the mosaic data. There is a north and a south region from NGC 1097, and we are downloading this. So as you see here, this took 1 minute. Depending on how busy Colab is, or your Jupyter Notebook, your connection, that can take quite a while, because we are downloading here an entire bundle of all the uncertainty maps, the real science maps, for all the filters, for all the 5 filters we have, and that can be big. So be careful of that. So then we are opening the catalog, and we have 2 catalogs for each galaxy. No, we have 4 catalogs actually. We have one for human, class 1 and 2. I will tell you later on what class 1 and 2 and 3 is. And for class 3, we have separated catalogs. And then this times 2, because one's human classified and one machine learning classified. And you can scroll along here, look what is in there. We have all the fluxes, all the magnitudes, some more informations, some flags. This is all described in our paper in quite deep detail, and also in a README file, which is coming with the data release. And now we can do some, why is it? Okay, and now we are just like loading like positions, colors, some magnitudes. I think this is not black magic what I'm doing here. And yes, so now, after we loaded some of the data in there, we are loading now, why is this? Why is it not? The screen is not updating anymore. What did I do? Did I somehow pause it or something like this? Stop. It's still, okay, I think this computer here actually, or I don't know actually. Screen share.
It could be the one that's actually presenting the display.
Can you share, am I sharing the entire screen?
Yeah, I think the, but this still shows sharing, so I think that's possible, because it says it's still viewing Kristen's screen.
Which we stopped sharing. So
Yeah, exactly.
Cool.
WebEx issues.
All right, sorry guys.
Have I told you that Zoom is better than WebEx? For those who work at the SDSCI. just telling you.
Okay. It still thinks it's viewing my screen, even though I haven't. Yeah.
Yeah.
Is there just like a text file with the names of all the NGC galaxies?
So it's an FETS file?
Oh, it's a FETS file.
If there is a name, the text file.
Because it's not.
I tried to find the CSV for like the table with all the RA index and stuff.
Yeah,
but
okay, good.
Of
like,
the galaxies or of the?
So I like just like.
Of all the galaxies.
Is there a way to like automatically download the entire data set? Is what I'm asking. Oh, okay. So you'd have to like do it one by one.
Yeah, I mean.
I'm scrolling now.
Yeah, it's not.
Yeah.
It's not scrolling.
It is possible, but it's not automated or supported. But there's also a table that provides the sample of galaxies. So like, if you go to the Google web page that I showed, There's a roundabout way to get that table. It's in the ALMA data release that has all of our galaxies. You'll find the names of each galaxy there.
Wow.
But
We could try now.
we can open
I
the
have my
Slack from here to
microphone.
get that link. Or
Is it working now?
sometimes.
Sometimes.
Are there any other questions? This question was about trying to just download the entire data set. You're talking about across all 4 facilities, right?
Yeah.
Or just, oh, Muse, yeah.
So what you can actually do is, or what I would say, so for example, okay, this is now for the images, unfortunately, but for the link is always the same to download a bundle. You just change the galaxy name, and the galaxy name you can access through, for example, our paper. There are like, these will be also delivered in machine readable, so you have like a table with all the galaxies, or just if you have just like some galaxies you want to access, you can just like run through this. The table themselves, they are just a few kilobytes. They are not big. I mean, they are big, large tables, but the images, that's what is really taking time. Okay, is it? No, yeah, I'm not running here like any cells. Okay, so we are, okay. We are back in business. And now we are, so I just like tell you what is in this cell here. We are now opening the HST image, and we're just converting from electron counts per second into Jansky, and also opening the uncertainty maps. So if you want to do science with our images, here you have science-ready images, and you can simply, this is what I'm doing now, just like plot them, and I'm plotting, and I'm overplotting the coordinates of class 1, 2, and 3 clusters. And what you say, as I said, like I will tell a little bit more about 1, 2, and 3 clusters. As you see, class 3, for example, you see them in the inner ring of this galaxy. A little bit at the end of the bar, you see class 1 objects fairly distributed over the galaxy, and class 2 a little bit in between, mostly on the ring and also at the edges. So what are class 1, 2, and 3? So we take just like random 1, 2, and 3 objects and we plot them. And yes, class 1 clusters are very symmetrical, so they are spheric. These are, for example, a globular cluster would be a class 1 object. A class 2 object can be a little bit elongated, can be a little bit disturbed, can have like some features on the side. That's a class 2 object. And a class 3 object is something which has multiple peaks. So when we think about like clusters, then we know, okay, class 1 object can be way older or something very, very bright and very massive. Class 2 can be way more younger, which has still like some tidal features, and class 3 objects are normally the youngest objects. They are like still having like associations with themselves, and they are not yet like really in an equilibrium. So I think, I don't know how much time I have or something like this. Okay, so we showed this before. I'm here just downloading also the BCO3 stellar evolution model. To just show now a color diagram with the different clusters from this galaxy, and I will directly scroll to the figure. So if you have questions on how I'm plotting, how I'm like accessing the data, please contact me. So what we see here is, I can't do this smaller, right? But it's like, okay, I will just tell you what is what. So class 1 is red again, and when we see just like the blue line, this is our stellar evolution model. Like it's starting at 1 mega year and like it's ending up here at 13 giga years. And we have this for like, and also like the very old model I show also for 150 solar metallicity, so low metallicity. And what we see here on the very bright, on the very old stage is there are mostly class 1 objects. And as I said before, yeah, class 1 objects, they are, for example, old globular clusters. They're exactly there. When we look at the blue objects, blue are the young, like the class 3 objects with multiple peaks. They are mostly associated with like young ages, and when you just take into account that we have also a reddening vector, that the things which are reddened are shifted into this direction, we see, okay, they are very young and they are just like dust reddened. And class 2, for example, they are a little bit in between. So what we've shown in our paper, that you can use the classes and where they are in the color diagram, are kind of a surrogate to understand at what evolutionary state is the stellar population of these clusters. You can, and then like see where they are in the galaxy. You can directly do science with this. The last thing is we will now plot just like randomly 5 class 1, 5 class 2, and 5 class 3 objects. No, sorry. Yeah, so we also on my poster we showed also like this young cluster regions, the middle-aged plume, and the old globular cluster region locus, and we are just like plotting 5 objects of each region. And when we are looking, for example, on the YCL, this like young cluster locus, we see a lot of blue objects, we see a lot of multi-peak associations, which is definitely a good, gives us a good idea that these are young. When we also see at the background, we see, okay, the MAP, the middle-aged plume, is already a little bit older and way more isolated. And when we now see at the old globular cluster regions, we definitely see also here in the in the RGB image that they are redder, way older, and yeah, they are true old globular clusters. Okay, and I'm so far done with this. If there are any questions, you can ask them now. Yes.
Hello?
Just confirming, is the archive.stsci website only for the HST and JWST data products? Are the ALMA and the Muse data products located elsewhere?
Yeah, so she is also showing that, like with Muse and ALMA, there are like not all of our data products we have and we show sometimes in our presentations are yet public, but I think ALMA, everything is public, right?
I'll put the other links to the ALMA and the Muse data in the Slack.
Yeah. Okay.
Any other quick questions? I'll show one more notebook, but I'll just do a couple things from it to make sure you've got time.
Yeah, also when you have like a very specific question, for example, hey, I want to use your code, your cluster catalog, just email me and I can very simply update the Jupyter notebook, insert some parts, or give you other code examples if you are struggling with like accessing our data.
Yeah, so just as an introduction, this is the next one, the Multi-Scale Stellar Association notebook. So I have just linked here the papers if you want to actually get the details on what the data sets are from the papers. So the Treasury Program paper, the Stellar Association paper, this is the Muse Nebular Catalog paper. So I show where to download the Muse, their catalog, and then the Treasury Program for web. And just as a other note, since this is sort of like Google Colab, if you've never used that before, if you ever want to, you can save a copy to your own desktop. You can save it just as a Jupyter notebook. You can save a copy elsewhere. You can also open a notebook and you can say, search from someone's GitHub. So like this is Dave's. He has one that just does Sundog that we won't have time for. So you can just search their GitHub name. And these are all in our GitHub thing. So if you want to go by later and grab new ones. But the links I gave should work even as we update it. So just as a note on how to get more things from Google Colab. So then that's where it's at, and you can just open it, even if you don't have the link. If you just know someone's GitHub name, you can search by that. Yeah, so this is, again, just loading stuff. I won't go through that. I'm going to be looking at 1566, so I just loaded the pretty press release image so you can see what we're looking at, because pretty images are nice. And then this shows where to get the HST and JWST public data. And again, this is the STSCI link that you can see the data page that Dave already showed. And so if you have that, you can just download the data bundles here, and in Google Colab, it just downloads it locally, and then you can unpack your bundles. And here I just show what it looks like if you plot sort of the HST, U-band, and V-band, because we have 5 different HST bands, so you can see the difference. And then this is what the web data looks like. So the pretty images you got if you came on time are all this web data for the first 19 galaxies. So you can definitely see you're seeing different structures with the web data than you are with the HST data. But the clusters and the associations we're showing, those data catalogs were all defined from our HST data. So they're where things are, they were optically located, and then we can look and see what, say, the dust properties are by looking at the web data. And so this is a page that shows, which we talked about. So this shows all the things public data. Actually, let's just open that. We'll see if it takes me. Leaving. Okay, well, maybe that won't work in real time. There's just a Gordy there. Okay, so that is the link to take you to all of the other things data. And this is how you grab the stellar associations. So when you grab sort of the bundle for one galaxy, you're getting a lot of things because there's all the different size scales from 16 parsecs, 32 parsec scale, 64 parsec scale. So there's different size scales of the association. And then we had 2 different ways of tracking the data. We found the stars based off of their V-band data, and then we also found the stars based off of the NUV band data. So depending on what you want to do, you can grab that catalog. The details are in the paper because we don't have time. But if you just load in then one of the stellar association catalogs, this is just all of the different regions. So then you can take, this is sort of a FITS image of all of the regions and where they are. And then you can overplot that on real data to see what it looks like. But first, this is also the data file. So just like Daniel showed, there was a data file of all the different information of the different regions for clusters. We have that for every association region as well. So we have all the fluxes that have already been measured. And then we also have our SED fits. So for the estimated ages and masses, and reddening based off of those stellar population models that Daniel was showing. Those are all of those properties for, well, at least 4 galaxies are already up for the associations, and more will be up later. So this is just an example of where to get the Muse nebular catalogs, like you were asking. So that's the webpage you go to, and then this, I just downloaded one of the nebular masks, and that's what this looks like. So it looks different from the regions that you'd use, where I define them based off of the star locations. This is using the H2, the Muse data and kind of definitions of where they think the H2 regions are. And then because we have estimated ages for these regions, just as an example of something you can do by combining the data files with sort of where the regions are, you can divide them in sort of age bins, and then we do some fancy matching to match sort of the web data to the HST data. And then you can overplot based off of like color coding the age regions. So this is one of the smaller scales, so you can see it kind of looks tiny on the screen, but you know, blue is younger, green is intermediate, red is old. And then if we kind of zoom in, you can see what that looks like in the HST versus the web. So like one thing, so I just kind of zoomed into an interesting region. You have some intermediate here surrounded by some young ones. And then if you look at the web data, you see the intermediate are kind of in this hole, and then these young ones are kind of on this edge. And you see it's, you know, the dust lanes are different from where you have these dark dust lanes in the HST, but they're bright in the web. So you can kind of then use that to figure out, you know, what's the dust properties and where I was finding my stars. And this is just bringing in what Brad was talking about before. Is we also have the Sundog server, which makes the pretty 3-color images. and you can interact with that in Python as well by downloading the pretty 3-color images and overplotting things. I'm just going to scroll to the end. So that's what it looks like when you do kind of where the regions are downloaded from the Sundog visualization server. So then these are the bigger scales, as you can see. So yes, that was very quick because we're at the end. But you guys have access to that now, and so feel free to Slack us or email us if you have more questions.
Even later this afternoon, we'll be around if people want help going through the notebooks. And I guess we should switch over to Ryan now. If there's time after you're done, we have a fabulous movie that the public people put out showing all 19 of our galaxies going between Hubble and Webb. So maybe after everything's done.
So the notebooks that have been shared on the Slack channel, do remember that the Slack channel notebooks would not be accessible after like a few weeks, 2 weeks, after 2 weeks or so. So save it right now, like copy it into somewhere offline so that you can access it at a later point as well. And like basically like there's the cafeteria and the Mueller CafeCon is available for you if you want to just try it out, and the Fangs team will be around. So if you have any questions later too. Oh yeah, so we can also add things to the website. So what the Fangs team are going to share with us, we'll add it to the Symposium website as well. So off to Ryan.
So I think I can just share my screen from my laptop and it'll show up.
Yeah, I think that's easiest, yeah.
Okay. Okay. Thanks.
Once you're done, the switch to turn it on is right in the middle of that. I have to turn it on.
All right. Hello, everybody. Yeah, so I'm just going to take a little bit of time to, let me see, close some things that are popped up in front of this for me real quick. Talk a little bit about ISM property determination. Oops, sorry. There you go. So we had a lot of discussion on different days about different properties that one would derive from the ISM. In particular here, I'm going to focus on the ionized ISM, and this definitely has a lot of relation to, for example, the discussion of metal abundances in galaxies that we talked about. And there we go. So what we'll be talking about, primarily how to derive properties of the warm ionized ISM. Often we think of H2 regions for this. A lot of these things actually do apply to things you could derive for example, AGN narrow line regions if you want. It's a lot of the same physics as long as it's photoionized gas in thermal equilibrium. But I won't be talking about other phases of the ISM, so sorry, we certainly don't have too much time. And then, particularly, we mostly think of gas ionized by massive stars for this, but there is some overlap. So, we think about taking a spectrum of some source. The rest optical spectrum here could also be, the ultraviolet or other areas of the spectrum, and we want to convert this and do physical properties. And the reason we can do that is because different physical properties set the strengths of these different emission lines in a spectrum like this. So what physical properties? We have things like the density and the temperature of the gas or of the electrons in the ionized gas. The metallicity or the abundance pattern, because of course it's not all just one metal, so we can have different patterns of abundance. And then some ionization state properties. So we have what's doing the ionizing, in particular the ionizing spectral shape. So that's basically what is the number of photons as a function of energy, right? So that's very different for an AGN versus an O star versus a lower mass star, right? Or for a very young cluster versus an older cluster. Ionized production rate, which mainly sets how bright or faint these lines is, kind of changes the normalization, but that's important for many astrophysical contexts. And then the ionization parameter, which is kind of a, pun intended, I suppose, nebulous thing that most people don't have a great intuition for what it is, but it's essentially, if the ionization parameter is higher, then for a given element, a larger fraction of it is in a higher ionization state versus a lower state. So if you increase the ionization parameter, more oxygen is doubly ionized versus singly ionized. And this really depends on the the ratio of the intensity of the ionizing photons to the density of the gas. So it's complex. It depends both on the intensity of the radiation from the source, but also the geometry and the density of the gas around the regions. It gets lumped into this parameter. And so we can break this up into a few different classes. We have just the basic physical properties of an ionized plasma, the electron temperature and the electron density. We have things having to do with chemistry, metallicity, abundance pattern, and then things having to do, like I said, with the ionization state. Some of these are super interesting for us for astrophysical purposes, right? Things like metallicity or things like the ionizing photon production rate that we might want to know for, figuring out if galaxies drive reionization or something like that. And then some of these are really more necessary if you want to, make calculations from theory side. So if you know the temperature and density of the gas, you can make a bunch of fundamental atomic physics calculations. So I would say these are less astrophysically interesting, but from a diagnostic standpoint are really powerful. But I think at this conference we had most discussion of metallicity and abundance patterns, especially on the session on Tuesday and Wednesday. So we heard this some in Danielle's talk and in some of the other talks. There's a few methods that we use to derive ionized gas phase metallicity. We have this so-called direct method or temperature-based method based on detecting these auroral emission lines. We have the so-called strong line calibration method where you take some objects where you have this direct metallicity and you correlate the ratio of bright lines, and then you can use this relationship on huge samples of galaxies without needing really deep spectra. And then we have a theoretical approach where you use photonization models, where you stick in an ionizing source and some gas properties, and you vary those properties, make a big grid of models, and then you have a prediction for the brightness of different emission lines as you vary these various physical properties I just showed. Now, we tend to think that the direct method is kind of the gold standard or the one that you would like to use if you can. Of course, the drawback is you need very deep spectra to use this method. So, even in the local universe, there's, thousands of objects with such measurements, but not millions or hundreds of thousands like the full SDSS sample, right? And at high redshift, we're just getting into, samples of tens rather than singles, right? So, but let's dig into this a little bit. Why do we care about the temperature? We talk so much about, we want to know the temperature of the gas. Why do we care about it so much? So let's review a little bit of theory for how this works. If we want to think about how bright an emission line is, so the luminosity of a line, for example, like oxygen 3 5007, this is basically going to depend on the density of the ion, so the density of the O2 plus ion, for example, the density of the electrons, and then this epsilon, which is called the emissivity, which depends on temperature and density, and basically tells you, how much photon emission will you get at a given temperature and density per unit ion, essentially. And you integrate this over the volume of the ionized gas. That's essentially the luminosity of the emission line that you have. And so the electron density times this epsilon, the emissivity, is essentially the emission power per unit ion. Now, this is a plot from Yu-Guang Chen's talk. This shows the emissivity as a function of temperature for some different lines. So black is H beta. The solid ones are different oxygen 3 collisionally excited lines, and there's some infrared lines on here as well. The key thing here is that the collisionally excited lines, the metal lines, are super, super strongly dependent on temperature, right? And so that emissivity that was in that equation, you need to know the temperature if you're going to know the emissivity. And again, over the span of temperatures that H2 regions at high and low metallicities span, which is about 5,000 to 20,000 Kelvin, you can see some of these lines change by 2 to 4 orders of magnitude in the emissivity, right? So if you want to be able to predict line brightnesses, you need to know the temperature with some degree of confidence. So now, let's think about two lines, because we typically use line ratios as diagnostics, right? So if I have some line with the subscript I and a different line with the subscript k, if we take the ratio of those lines, we can just kind of get rid of the integral for simplicity. So that's just, the equation for luminosity just divided by each other. Of course, electron densities in both, that's going to cancel out. So you have the ratio of the density of the different ion species, and the ratio of the emissivities for those ion species, which is, of course, as I showed, a strong function of temperature. And if you flip this around and you, instead of solving for the luminosity ratio, you solve for the ratio of the number of densities, that's basically an abundance, right? Then that's equal to the brightness ratio of the lines divided by the emissivity ratio of the lines. And we could do this for an actual species, so say like doubly ionized oxygen divided by hydrogen, O3 5007 over H beta, and the emissivities of those lines as a function of temperature. This is the direct method, okay? So like that's why it's powerful. If you know the temperature, you can calculate these emissivities, and then you can convert brightness ratio to number ratio, and that's the chemical abundance, okay? So like that's why temperature is such a powerful diagnostic for us here. One thing to note, typically these abundances are number density ratio, so that's what I have here. In some contexts, their mass ratio, should just be careful when you're reading a paper, you know which one it is. Okay, so let's look at an energy level diagram of doubly ionized oxygen, O3, that we've been talking about, right? So we have our strong lines, right? 5007, 4960, 3 to 2, 3 to 1. And then we have 4363, the auroral line, right? 4 to 3, okay? And you can think of the energy differences relative to the ground state, about 2.5 eV for the strong lines and about twice that for the auroral line. And Danielle talked about this a little bit, but the reason this is a temperature diagnostic is because these transitions have a different upper energy level. So they take a different energy electron to collisionally excite it from the ground state up to the level where it's going to emit one of these photons, right? So the brightness ratio of two transitions with a different upper energy level, where there's a reasonably large gap in energy between those two upper levels, is why you get temperature sensitivity, okay? So 4363 to 5007 ratio essentially tells you the ratio of electrons with greater than 2.5 eV to the number of electrons with greater than 5.4 eV energy, right? And we assume this is in thermal equilibrium, so it's a Boltzmann distribution, so temperature tells you the electron energy distribution. So that's how we get the temperature from ratios of lines. And so you need these upper level lines that are the auroral lines to get this diagnostic, but they're faint because they're higher energy levels. So there's a lower number of electrons that can excite them up there, so they're fainter lines intrinsically. So this is just a plot, and I calculated this with PyNeb. I'll show very briefly in a few minutes how you can do this. So this just shows the strong line to the auroral line for different species. So log of the ratio versus electron temperature, O3, sulfur 3, nitrogen 2, et cetera. And of course, you see that log is 2 to 3, so that's 100 to 1,000 times brighter, the strong lines relative to the weak lines. But you can see that if you get to high electron temperatures, it's more like 30 to 100 times, right? So it's much brighter at high temperature, and the auroral lines are much, much, much fainter at very low temperature when you're close to something that's like solar metallicity. So we also care about density. That's in that equation too. It turns out the density is typically not a big deal unless the densities are so high that you're approaching the critical densities of the lines you're looking at. But we can get this from different doublets of lines where instead of, so they have a different upper energy level, but they fall to the same lower energy level. And so the difference in critical density between these two lines allows you to have a density sensitivity here. So sulfur 2, oxygen 2, these are some of the typical doublets that we can use to derive the electron density. So there's some of the UV, there's some of the optical, but we have these different diagnostics to get density. Some of them are different, sensitive to different density ranges because of the range of critical densities for these transitions. So, you might want to be careful that, like, if you're using, sulfur 2, for example, it's really only sensitive to densities less than, a few thousand. So if your object has a density higher than that, it's not going to tell you any useful information. So this just shows, like how much does the density matter? So this is the O3 5007 to the auroral 4363 ratio as a function of temperature for different densities. These top lines, you probably can't tell the difference. That's going from 1 all the way to 10,000 for density. But this bottom line is 10 to the 6 for density, and you can see it affects things a lot. And again, if the densities get higher than the critical density of one of these lines, That's when density makes a huge difference, right? So most of the time, the normal objects we're looking at, we're used to densities of 100, several hundred, maybe 1,000. So this is not a big deal almost all the time. But interestingly, at very high redshift, we've seen in GNZ11, we saw in Massimo's talk about the Godzilla cluster, we're seeing these things that might have densities of, say, 1 million per cubic centimeter, where collisional de-excitation, they're above the critical density, is important. So like, we might not be able to just ignore density at high redshift, but most of the time, you can basically ignore the density dependence. Okay. So quick how-to for direct methods. You just kind of go through what I just said. Derive the density from some doublet, O2, sulfur 2, something like that. Derive the temperature from an auroral line. Calculate the abundance ratio by dividing the observed brightness ratio by the emissivity, which you can calculate because you know temperature and density. And the way you calculate these, it's basically atomic physics. It depends on the energy levels, the collision strengths, and the transition probabilities for all the different levels in the atom. And PyNeb has coded this up and has data sets, so you don't have to solve a bunch of linear algebra equations yourself to do the calculation for the emissivities. One caveat, you do this calculation, now you know O2 plus over H, but O2 plus is not O, it's not all the oxygen, right? So you need to worry about what we call an ionization correction. How do we go from one ionized species to like all of the oxygen, right? Now, oxygen's nice to us because we have lines of both O2 and O3, so we can do this for O plus and O2 plus and add them together. And O3 plus, et cetera, takes 55 plus eV photons. So for most stellar populations, they're not producing those. So that's basically all the O in an H2 region. So that's kind of nice for us for oxygen, right? But for pretty much all the other elements, we very rarely trace more than one or maybe two ionic species, but that's not all of them, right? So for example, neon abundance, you could do neon 3 to O3, you have neon 2 plus over O2 plus. How do you get to neon over O, like the total abundance? So you have to do some correction that accounts for these unseen ionization states. So people have published papers where you use grids of photoionization models to calibrate what's called the ICF, the ionization correction factor. This can be really uncertain. So for example, over here for neon, this is as a function of basically the ionization fraction for oxygen. So what fraction of the oxygen is in O2 plus? You can see at low ionization, there's a huge spread in the ionization correction as a function of the parameters in the models, right? And it's smaller up here, right? So this is a systematic uncertainty on abundances. The more ionization states you measure, the less uncertainty you have here. So here, it's sulfur and oxygen, but you've measured two ionization states for both. You can see there's very little spread there, right? So that is a an asterisk. And the other asterisk is what temperature do you use in the direct method? So we know that different ions live in different spatial regions within the H2 regions, okay? Low ionization species will be near the outside parts of the H2 region, so O2 and 2. These are things with ionization energies roughly 10, 15 eV. High ionization things like oxygen 3 will be mostly towards the center of the nebula, 30 to 40 eV. And then things like sulfur 3, carbon 3 are kind of halfway in between. And there can be temperature structure in the nebula where the temperature out here is not the same as the temperature in the center, right? So we can measure this from different auroral lines, like oxygen 3 traces the high ionization temperature. Things like nitrogen 2 and oxygen 2 trace the low ionization temperature. But you don't always measure more than one of those. Sometimes you have to make assumptions for what the temperature in another zone is. This is local galaxies where you just measure both and you plot them against each other, see if they correlate. They correlate, but there's a ton of scatter, right? So this is also an uncertainty that should be taken into account if you only measure O3 and, for example, you have to assume an O2 temperature. There's a ton of scatter, and we also have no clue what these should look like at high redshift yet. So hopefully we'll be able to check that with JWST observations. Okay, so that can get us metallicity and abundance pattern. What about some of these other things? The ionization state is also astrophysically interesting because it tells us about, for example, the properties of massive stars, things like that. Well, if we want to figure out the ionization properties, we often have to turn to photoionization modeling. And one truth is that if you don't have very many emission lines, the solutions within a grid of photoionization models is very degenerate. If I measure some line ratios here in a BPT diagram, I mean, you can see with these grids that change just 3 parameters, it's degenerate for multiple solutions for this pair of line ratios, right? So with a few lines, it's very hard. A lot of degeneracy. Many factorization models don't have this degeneracy, but it's because they've implicitly assumed correlations between these different things. So be aware of what assumptions are in the models that you're using. If you can reduce this degeneracy, for example, if you measure a direct method metallicity, then you can fix that in the models, and you can fit for ionization state parameters unambiguously without degeneracy. So that's one option. And then the other one we've seen from Alessandro's talk, that if you have a lot of lines to fit to, not just 3 or 4, but say like 12, 15 lines, then you can break this degeneracy, especially if you have aurora lines to fit to as well. So you know, reference Alessandro's talk for fitting to a larger number of parameters. And then finally, let's talk a little bit about strong line calibrations. This is what we typically use, but you know, there's a lot of caveats that you need to be aware of when you use these things. So of course, they're based on a small sample with direct method metallicities, and we find these correlations, and then we apply it to big samples where we don't have to measure the weak lines. So the dirty secret about strong line calibrations is that most of the line ratios actually don't have any direct dependence on metallicity. They depend on these other things. They depend on the ionization parameter. They depend on the shape of the ionizing spectrum. They depend on the abundance pattern, say like nitrogen over oxygen. So for example, if you use N2 over H alpha to measure O over H, there is no O in N2 over H alpha, right? So you're actually measuring nitrogen abundance and assuming some conversion to get to oxygen abundance. Or like O3 over O2, right? There's no hydrogen in that. How can you measure O over H from that? You're really measuring the ionization parameter, and then some correlation between ionization parameter and oxygen abundance gives you O over H. So, so these things are really mostly dependent on ionization, different chemical abundance patterns, and then some of them that actually have O over H in the thing are also dependent on that. But whenever you use a calibration, it implicitly assumes that the properties of the calibrating sample are the same as the properties in the sample you're applying it to. So like this is what happens to O3N2, a common strong line that we use, strong line ratio versus over H. If you change the density, the shape of the ionizing spectrum, the ionization parameter, or the N over O, this line shifts all over the place, and your metallicities will shift all over the place too, right? So you need to be aware of that. So you know, any strong line calibration you use assumes that all of these correlations are exactly the same in the calibrating sample as in your sample. And I'll skip that. The other thing is that they all have a lot of scatter, 0.1 to 0.2 dex in oxygen abundance at fixed line ratio. And so for individual objects, you can never get an accurate metallicity with a strong line calibration. Never, okay? You can only get precise metallicities if you average over samples to beat down that scatter in these relationships. So be careful, like if you're just doing a single object thing and you get a metallicity, do not read into it much and keep in mind that it has a 0.1 to 0.2 dex systematic uncertainty just from scatter on that point. So we're pretty close to the end. So people may have downloaded the Python notebook that I put in the Slack. This just goes through some simple examples with PyNeb of how you can calculate these things. And I guess I can run through this super fast because we only have a few minutes. Should be able to run this. It's just NumPy, Matplotlib, PyNeb, and AstroPy. So you have to basically, make these objects that are different atoms, recombination atoms for like hydrogen or helium, for example, or collisionally excited atoms for oxygen 3, oxygen 2, things like that. That's what you use to do the calculations. So PyNeb has all the information about the atoms in here, right? So you can do things like print the transitions and the energy levels. This could be helpful. You can also change the atomic data that this is based on, right? Because different people have calculated these collision strings, transition probabilities from different sources. So this line here basically prints all the different oxygen 3 data that you can choose from in PyNeb. You might need to change this. For example, the one up here is only a 5-level atom. You can see it only goes up to 5 to 1. But if you were going to do the UVO3 line, that's a level 6 transition. It's not in that data, right? So you might need to change the data to be able to have a 6-level atom where you could access those data for those UV lines. Okay, so the most useful part of PyNeb, what it's really built on is really this get emissivity function. So like that's that emissivity thing I was talking about earlier. PyNeb, with the atomic data that's in it, can calculate this where you input a temperature and density, select a wavelength for a certain atom, and it will give you the emissivity. So you can calculate the emissivity ratios. For example, here I've just calculated the H alpha over H beta and the H gamma over H beta ratio for 10,000 Kelvin gas, right? I mean, this is what we use to do dust corrections, Balmer decrement, right? But these things depend on temperature, right? So like, what's the Balmer decrement? 2.86? Oh, that's great. What if I'm in a high metallicity region with 5,000 Kelvin? Oops, that's 50,000. Oh, now H alpha over H beta is 3.04, right? So like, maybe we shouldn't, always assume the same amount. So you can do this for hydrogen, but you can do this for any other atom. So I will say a great part about this, like if you're proposal planning, right, you're going to do some spectra. You need to estimate how bright some emission lines be, but like they're not detected in your sources right now. Like you want new data, right? You can calculate emissivity ratios, multiply them by some assumed abundance pattern, and you can estimate line ratios based on the atomic data in PyNeb. This can be really useful if you have some data with like H alpha and O3 and you want to get UV and carbon 3 or something, you can make estimates for what the line ratio should be based on some of this. So that's useful. Some of the rest of this shows you how to do the temperature and density calculations. This is basically just using the get emissivity to plot these strong to auroral ratios as a function of temperature. I showed those earlier. Really easy to make those sorts of plots. So I included this catalog of H2 region line fluxes if you want to try out some of this stuff for calculating abundances or different abundance patterns. So there's basically this get timden function you use to do either the density or the temperature. So if you specify a density when you call this function, then it will calculate the temperature, and then vice versa. If you specify a temperature, then it will calculate a density. So you just have to do this for whatever atom, ion you're using, specify a temperature or density, and then specify the wavelength of the denominator and the numerator for the line ratio that you've input. So we can calculate this here and get densities from sulfur 2, oxygen 2 for these local H2 regions, something around 100. We can take the same function and specify a density instead of a temperature, and then use the appropriate lines. Here it's O3 4363 over 5007, and get a temperature. So we get something around 10,000 Kelvin. We can do this for other things like O2 or nitrogen 2 auroral lines, also get temperatures. And then, final thing, if you want to get to the metallicities, you take the temperatures and densities you calculated above and put them into this get ion abundance function. And so here you put in a line ratio relative to H beta, and then you put in the wavelength of the numerator, and it will calculate the abundance. Now, just to show you that this is essentially the same as the emissivities, you can also do this by just calculating the emissivity ratio and then dividing the observed line ratio by the emissivity ratio, just like I showed you in the slides. And if you look, you get the exact same number. So this is basically just a wrapper for calculating the emissivities separately by yourself. So I think we're out of time. So if people want to look through the rest of that catalog, you can play around with this stuff. It can be really useful for planning proposals, like I said. Yeah. Oh, okay, yeah, that's fine. Well, I mean, there's honestly not like too much more. So that's the O2 plus over H abundance. This next frame does it for the O plus over H based on the O2 doublet. So we can run that, calculate that. And then, of course, if you want O over H, you just add these together, and we like to add 12 to it for some weird historical reasons, right? So, then we get a metallicity that's roughly 50% solar for this galaxy, right? Now, one thing you can see is, if you want to go back and mess around with this, you can see how much the temperature affects the outcome. So if I take the temperature we assumed for O3 and let's, change it by 2,000 Kelvin, right? So we got 8.2 in the first calculation. And now I get 8.6, right? So that's like up to almost solar metallicity. And then if we go the other way, instead of 8.2, now we're down to 7.9, right? So plus or minus a couple thousand Kelvin can be the difference in an order of magnitude in the abundance that you infer, right? So these things are very, very sensitive to temperature. So that's why it's so important for these calculations, and that's why we go on and on and on about the auroral lines for the direct method metallicities. So down here, this next one, basically instead of doing oxygen abundance, we can do relative abundances of metals, right? So for example, first nitrogen 2 over oxygen 2 gets us M plus over O plus, or neon 3 over oxygen 3 gets us neon 2 plus over O 2 plus. So we can do that calculation as well. Note here that I've assumed a different temperature for neon 3 and O3. I used this TIM high, which was set to the O3 temperature. And I've used a different temperature for the N2 and O2 calculation, which are low ionization. So I used TIM low, which we had here set to the nitrogen 2 temperature, right? And so that is important, that when you do this for a certain ion, think about whether it's a low or high ionization ion and use the temperature that should correspond to that appropriately, because they might not be the same. I mean, sometimes they're close, but sometimes, here the O2 temperature disagrees with the nitrogen 2 temperature pretty significantly. There are some reasons why that's hard to do at redshift 0, because there's a lot of atmospheric absorption at those O2 wavelengths. And then this last part is basically just doing the same calculations, but just looping over a whole catalog of H2 region line fluxes, where we can do this for a sample of H2 regions, save it in an array, make a few plots at the end. So here we'll just do this. So for example, this is just a BPT diagram. So O3 over H beta versus N2 over H alpha, color-coded by the metallicity that we just measured with the direct method. So you can see this trend where when you're high O3 over H beta and low nitrogen 2 over H alpha, tends to be lower metallicity, and this metallicity basically increases as you go down and to the right. This is the metallicity sequence along the BPT diagram for star-forming regions or galaxies. And then here's just a plot of electron temperature versus metallicity. So this is generally what we expect, that low metallicity objects are hotter because they have less efficient cooling in the gas with a smaller amount of metals, and higher metallicity objects tend to be cooler, more metals, more metal cooling lines, you get a lower equilibrium temperature. So just a couple of quick plots there. You can plot lots of stuff correlated against each other. Yeah, so that's a quick overview. I'll be around the rest of the day and during the coffee break, so if anyone has questions or wants to talk to me more about that, I am happy to discuss more, and you can also just send me an email at some point or something as well. So yeah, sorry we didn't have too much time to rush through that a little bit, but thanks for listening, and hopefully people learn some stuff that'll be useful for them in the future.
Okay, so as Ryan said, he'll be around here in the area. So we'll reconvene at 3 o'clock? Yeah. We'll be here for the next Hubble Advanced Science Products workshop at 3 o'clock, right here. Spectral products.